In these next couple problems, we will use the direct comparison test to determine whether certain series converge or diverge. In this first example, we have the series n equals 1 to infinity of 1 over n to the 3 over 2 plus 1. In part A, we want to find a geometric series or a p-series where you can compare b of n to. Note that using the direct comparison test with a geometric series or a p-series is straightforward because we have theorems that tell us when a geometric series converges and diverges, and same with p-series. For this problem, observe that the series that we are looking at is very similar to a p-series where p is equal to 3 over 2. And so the most obvious choice is to set b of n equal to the p-series b of n equals 1 over n to the 3 over 2. For part B, we need to set up inequalities to compare our a of n and b of n. And to do this, we can compare the denominators of the two series. Notice that n to the 3 over 2 plus 1 is greater than or equal to n to the 3 over 2. And thus, the series with the bigger denominator is going to be the smaller one. And thus we see that a of n is less than b of n. For part C, we need to use the direct comparison test to determine whether the series converges or diverges. Here we see that our a of n is less than or equal to b of n. And we also see that the series n equals 1 to infinity of b of n converges by the p-series theorem. And since we know that a of n is less than a convergent series, it must be that in the series n equals 1 to infinity of a of n also converges by the direct comparison test. So now in problem 2, we have the series from n equals 2 to infinity of square root of n over n minus 1. For part A, we want to find either a geometric series or a p-series to compare this to. Now for this one, we want to think about this similar to a p-series. If we think about a p-series similar to this for b of n, we get a square root of n over n. And we can simplify this algebraically to get 1 over the square root of n, or 1 over n to the 1/2. Now for part C, we need to use inequalities to compare our a of n and b of n. Comparing the denominators, we see that n minus 1 is less than n. This means that the square root of n over n minus 1 is going to be greater than the square root of n over n. And so we get that our a of n is going to be greater than or equal to our b of n. Now for part C, we need to use the direct comparison test to determine whether our series a of n converges or diverges. And we observe that our series n equals 1 to infinity of b of n diverges by the p-series theorem because our p is equal to 1/2, which is less than 1. And because our series a of n is greater than or equal to a series that diverges, we know that the series n equals 1 to infinity of a of n diverges also, and this is by the comparison test. For problem 3, we have the series n equals 1 to infinity of 1 plus sine of n over 10 to the n. To find a series to compare this to, we observe that this is similar to a geometric series. The geometric series I'm going to use is 2 over 10 to the n. Now the reason I had a 2 in the numerator is because for part B, when we want to find our inequalities here, we see that sine of n is less than or equal to 1, so 1 plus sine of n is less than or equal to 2. And this allows us to see that 1 plus sine of n over 10 to the n is less than or equal to 2 over 10 to the n. And so a of n is less than or equal to b of n. And so in part C, we observe that the series n equals 1 to infinity of b of n converges because it is a geometric series with r equals 1/10, which is less than 1. And thus we see that the series n equals 1 to infinity of a of n must also converge by the comparison test.